Good afternoon, ladies and gentlemen. Thank you for attending this course on wood design. I'm Dilip Khatri. I'm a structural engineer in Los Angeles, and I'm pleased to present a little practical course here to help you with understanding how to work with wood. Wood design covers approximately 85% of the floor space in the United States. All of our residential structures, practically all of them, and a significant portion of our commercial space are constructed out of wood buildings. And it is actually the area which most engineers have the least amount of technical training when they're going through their college education. And they have to learn this subject matter in the field, if you will, or through internship. So I get a lot of questions on wood design, not just from engineers, but also from architects and from contractors. So I put this little short course together to kind of give you some of the basics, the fundamentals, and you could understand from there, and then we'll build on this as we go further. Let's take a look at the outline, and I'll give you a little overview of what we're going to cover. So the first thing is to understand wood design is called Type 5 construction. I want to explain what that means. And then I'm going to show you some really good textbooks. The best textbook that I can recommend to you is the book by Breyer, which you'll see the cover of that book come up. And that book has been the reference book for wood design for several decades. There's also the American Wood Council, which publishes a lot of excellent material. And then the codes and standards, which are covered by the International Building Code. And Applied Technology Council also offers some very good guideline documents, and so does FEMA. Let's talk about wood as a material, because wood is a very unique material, and it's important to understand the fundamentals of it in order to be able to design with it. If I take a look at a typical wood beam, wood being a natural material coming from trees, consists of grain. And so you have grain or fibers that are running along the length of this beam. And one property about wood which is really terrific is that if I try to stress the wood along the grain, if I pull on it with a tension force, this is called tension that is parallel to the grain. Wood is a fantastic material. It's very strong parallel to the grain. But if I try to stress it perpendicular to the grain, in other words, if I'm stressing it perpendicular to the fibers, wood is not such a great material. The wood will separate because it's very weak perpendicular to the grain. So one of the main things about working with wood is understanding this phenomena, that it is not like steel, it is not like concrete. It doesn't have exceptional strength in all directions. It has exceptional strength really in one direction, which we like to use. It's very easy to work with, and it's easy to cut, and it's light. So that makes it very easy to work with, and that's why we call it light frame construction. How does wood fit in with the building code in terms of type of construction? All of the buildings that are built fall into 5 categories. Types 1 through 5, and they are rated in accordance with their fire resistive capability. Type 1 being the best. That's usually a concrete building or a steel building with fireproofing. Type 2, non-combustible. Type 3, ordinary. Type 4 is heavy timber, which are made of wood but with very heavy sections. Type 5 wood, which is 90% of what we have, is split into 2 categories. There's Type 5A and Type 5B. Type 5A has a 1-hour fire resistant envelope, and Type 5B does not have a 1-hour fire resistive envelope. So if we look at a typical wood building, we have a system of columns, we have a system of beams, we have a roof system with rafters. In here we have shear walls, we have a floor diaphragm. The fire rating is the envelope of the structure, that if it has a 1-hour fire rating, that it doesn't mean that it's necessarily going to last for 1 hour. It just means that that material was rated in a lab to be able to provide 1 hour of fire resistance so that the occupants could get out. But be very careful interpreting that, because if you've ever seen a building under fire, you generally don't have anywhere close to an hour. You usually will have a few minutes to get out of that structure, because what's inside the structure that makes it combustible. But in terms of fire rating, that's how we describe a wood frame building. So all of these components interact with each other to transfer the loads from the roof to the walls, to the studs, and down to the foundation. That's what's called load path. And load path is a very important term to understand, because when you design a structure, if you don't have a way for the loads to travel and get down to the footing, then you have a missing link, and that structure is not going to be able to stand up. So architects who come up with fantastic floor plans and spectacular designs, but if we don't have a load path, there's something missing there. Here's a three-dimensional view of a wood frame building. We have ceiling joists, roof rafters, roof sheathing, and those loads are transferred down through a system of wall studs. We have wall sheathing. We have the floor loads transferred through a system of floor joists, which are then transferred through the rim joists and then transferred down to the first floor and eventually down to the foundation. There's a continuous load path. The load follows from one joist to the wall, down to the next wall, all the way down to the bottom, and eventually to the foundation. If we remove areas of wall, then we have to substitute that with columns. If we create large openings here, we have to substitute that with columns so that we have continuous load path. I know that when architects design buildings, they always like to have large open floor plans. So do I. But let me give you an example. Let's say you're designing a floor plan, and I'm just going to make this very simple. You design a floor plan, it's not rectangular, shaped in kind of an odd fashion, where this is all glass, because you have a spectacular view here. You're up in the Hollywood Hills or on the top of a mountain. So you design a floor plan which has all glass, and then you have walls over here. We'll put a couple doors in here, okay, to get in and out of the space. The problem with this design is that we're missing an entire load path where this glass is. We've got to put some columns in order to be able to create a system so that the system is balanced. Symmetry is very important in any building design. Now, that doesn't mean that every building has to be shaped like a square or like a rectangle. We can make plans like this work, but you need to be aware that you have load path that has to transfer from floor joists to columns and get down to the foundation. Always remember, continuous load path, very important. Probably the single most area where architects and engineers have disruption, because engineers like to have symmetry, architects want to have anti-symmetry or creativity. If I take my wood member that I drew earlier, and I take that wood member and I put it in a testing lab, and I subject it to a series of tension loads, and I graph that, I'm going to produce a stress-strain curve, which will look something like this. This is the load or the stress, and this is the deflection or the strain on my wood member. So I'm pulling on this wood member. The first portion of the zone is called the elastic zone. And this is where everything changes. Because at this point, which is the yield point, anything that I do before the yield point is recoverable. It means that if I stress it up to this point over here and I release the load, the member will go back to its original position. But once I pass the yield point, once my structure goes past that limit of proportionality, then if I release the load, it will not return to its original location. It will have a permanent deflection. And that's exactly what we don't want to have. Can you imagine if you're designing a building and let's take a simple example of a house. Here's my simple house, and it gets hit by a windstorm, and the building deflects, and it doesn't go back. Who wants to live in a house like that? So that can't happen. So we don't allow that to happen. And the way that we don't allow that to happen is we make sure that we never exceed that yield point. Because even though we have all this extra strength, we don't make use of it. We don't take advantage of it. We are only interested in having the structure return back to its original location. You can imagine if you're walking on a floor system and you overstress the floor system and the floor system deflects and it doesn't come back. Is that a useful floor? The floor is done. So we never want to go past this point. So what we do as engineers is we take that yield point stress and we divide by a number, which is called factor of safety. That factor of safety puts us somewhere about here. And that is our design stress. Because we don't want to take a chance. We're very conservative. And usually that factor of safety is at least 2. Sometimes it could be as high as 3 or 4. So we are only using, at the most, 50% of the capacity of that wood member. This applies not just for wood, but this is the same for concrete, steel, and for masonry. Specifically to wood, we don't want to exceed that limit. So we have built-in factors of safety just in case there's an overstress. And that's the reason you see very few failures occurring in most structures, because we have a built-in factor of safety. That's done on purpose. So by limiting our design stress, let's say we're using a factor of safety of 2. That means we're only using about 50% of the yield point capacity. So the entire structure will always perform in this envelope. And then maybe in some dramatic situation it might go beyond that, in an earthquake, in a hurricane, or in a tornado, and in some very, very extreme circumstances it may actually break. It may actually go all the way here and it'll tear. So we try to prevent that from happening. And so that's why we have factor of safety. And this applies for all wood members. It applies for the wood shear walls, wood beams, columns, trusses. We talked about load path. They all have factors of safety associated with them. What is the beam? A horizontal member which carries load vertically. Definition of a beam. And how does it transmit that load? It transmits that load to the columns or shear walls in the form of bending, which means it's going to deflect like this. And when it bends, the maximum bending stress is occurring at the center span. That's where your highest deflection is. So this is your maximum moment, your maximum bending stress. So when you're designing a floor system, keep in mind that when you're designing a system of beams, your span length, the longer your span, the bigger your beam is going to be. If I'm designing a span length of 20 feet, I'm going to be using floor joists that'll probably be on the order of 6 by 18 or 6 by 20, depending upon what the loads are, because that's a large span. And so a 6 by 20 is 6 inches wide by 18.5 inches deep. A lot of architects have an issue with that because that's too tall, it's too thick. They want to have a thinner span. So either I have to go with a different material, or I have to put in some column load in order to reduce that span length so that I can put in a smaller floor beam. So that's a beam. A column is a vertical member. A vertical member that takes axial load. And columns are separated into 2 categories: short columns and slender columns. Short columns also called non-slender columns. What's the difference? A short column has a different type of failure mode. This is my short column and my slender column. A short column, when it's subjected to axial load, will fail by compression, by crushing. It'll actually crush under the load. A long column or a slender column will never reach the crushing capacity. Instead, it fails by buckling, because at some point it becomes unstable, and so it'll snap. This is illustrated by a very nice sketch here that I have, which tells me for different types of end fixities what happens with different types of columns. So a slender column which has its rotation fixed at two ends will develop a buckling curve that looks like this. If it's pinned at two ends, it'll develop this type of buckling curve. If it's not fixed at one end, it'll have this type of buckling curve. So the capacity, if you do the design calculations on this and you graph this length here, which we call the effective length, if you graph the axial load capacity versus the effective length, the graph will look something like this. You have the allowable compression load, you have the effective length, and the curve looks something like this. And over here, you get the maximum capacity when you're a short column. And when you pass this, you become a slender column. And then there's usually an upper limit. You can't go past that upper limit. And that depends upon the type of wood. I haven't put any numbers in here because I'm just giving you the concept. But you can't have a column which is, say, 4 inches by 4 inches, a 4 by 4 that goes, 30 feet, for example, because it's too unstable. You've got to put in some lateral bracing. So there's a limit on how far you can make a tall column. And this is important for architects to understand, that you can't design, a complete column that's going to span from the base of the foundation all the way up 40 feet. I mean, it's unrealistic. And I've seen designs like that happen, and it's not possible. You have to remember that you have engineering limitations on your materials. If you're going to do that, if, for example, let's take this design. Let's say that my architect wants to create a bay window here, and he wants to have the height of the window going up 2 stories. Yeah, you can do it. I didn't say you can't. You're just not going to be able to do it in wood. You'll have to put a steel column over here and a steel column over here. So it can be done, but then you've got to go with a different material. You can't do it with wood because it's too much. The same thing goes for openings in the other direction and the substitution of shear walls. If you want to create all glass over here, I'm not saying you can't do it. Remember, I've never said you couldn't do it. All I'm saying is you need to think about it and engineer it properly. The most critical part of wood design, if you think about all the wood buildings, and I do a lot of forensic work, I do a lot of investigation on structural failures. It's been a big part of my practice for more than 25 years. You'll never see, or very rarely will you see, a wood beam failure or a wood column failure. What you see are wood design connection failures. This is probably the single biggest source of problems in buildings. The other thing you see extensively is water damage and termite infestation. And I want to show you some examples. Of course, you see a lot of wind damage, you see a lot of earthquake damage when earthquakes occur, but by far, if I had to pinpoint of all the wood failures that I examine, the top 3, the 3 big problems: connections, which is where my beam comes in to meet my column. This connection in here is a problem. It ends up with cracking, ends up with all kinds of issues. And the other one is wood damage with termites. And I want to show you an example of a couple of inspections that we've done recently of exactly what happens. And I'm going to try to hide the name of the property, but here's an example. This is on some balcony decks. And what we've done is we've taken the stucco away and opened up these decks in order to look at the condition of the wood. And you can see right in here, you can see the termite infestation where the wood has been completely eaten. You can see over here the base of the post is completely eaten. You can see the holes in the wood. You can see over here that the water damage and the termite infestation has completely warped these connections and has eaten away. You can actually see the fungus growing on the panel. This is probably the most telltale. You can see over here extensive termite infestation. This structure has to be replaced because the damage is so bad. You can see the extensive termite infestation. Here you can see extensive termite infestation, wood damage. That whole deck has to be replaced. And again, on it goes, one after the other. And it gets worse as you go to the connections. The interesting thing about these pictures is that if you look at the stucco, everything looks nice and clean. Everything looks pristine. But the minute you take the stucco off, you see that the entire structure, it's about ready to fall down. So what did I have to do in this case? I had to flag off the building. I had to tell them not to go on the balconies until we could go and replace this. And again, if we hadn't opened it up to go look at it, we wouldn't have a clue. This is probably the worst one. I think I'll stop on this one. Look at the condition of that beam. That thing's about ready to collapse. And again, not a sign of it from looking at the stucco. It's been going on for years. So, as a precursor, just to give you a little introduction, we'll talk more about wind damage and earthquake damage in another class, but I wanted to illustrate for you the problems with moisture, water damage, and termites, and specifically give you some basic introduction on wood design and how these three elements interact with each other: beams, columns, and shear walls. Thank you for attending this session.